Space is home to an incredible number of mysteries. We gaze up at the night sky, our eyes drawn to the twinkling stars, and we can't help but wonder about the vastness of it all. How many stars are there? How many galaxies are out there? These are questions that have fascinated humanity for centuries. One of the most mind-blowing facts about the universe is that we can only see a tiny fraction of it. What we observe, the stars, planets, and galaxies within our reach, make up just 5% of the universe. The rest, an astounding 95%, is shrouded in mystery, comprised of dark matter and dark energy. Dark matter, invisible to our telescopes, exerts a gravitational pull, holding galaxies together. Dark energy, even more mysterious, drives the accelerating expansion of the universe, pushing galaxies apart at an ever-increasing rate. These enigmatic forces remind us that we are still scratching the surface of understanding the cosmos. Our galaxy, the Milky Way, is a swirling city of stars, a vast collection of dust, gas, and billions of stars. Yet, it's just one among trillions of galaxies in the observable universe. Each harbors billions of stars, each a potential sun with its own planets. Even within our cosmic neighborhood, we encounter wonders that defy imagination. Neutron stars are so dense that a teaspoonful would weigh billions of tons. Black holes, where gravity is so strong that nothing can escape, lurk at the centers of most galaxies. The observable universe stretches out for billions of light years in every direction. Light takes time to travel, so we see distant objects as they were in the past. The most distant galaxy's light has been traveling for almost the entirety of the universe's existence. The scale of the observable universe is almost impossible to comprehend. Our planet, solar system, and galaxy are tiny specks in this vast cosmic tapestry. Yet, within this vastness lies the potential for life and other civilizations. The search for extraterrestrial life is driven by the sheer number of stars and planets. As we explore the cosmos, we are reminded of the universe's immense scale and the possibility that we are not alone. For centuries, astronomers could only marvel at the scattered stars visible to the naked eye, unaware of the sheer scale of the universe beyond. But with the advent of powerful telescopes, our cosmic horizons expanded dramatically. We began to see faint smudges of light that turned out to be entire galaxies, each containing billions, even trillions of stars. The question arose, just how many of these star-studded islands exist in the observable universe? Early estimates were tentative, based on limited observations. However, as our telescopes became more powerful and our techniques more sophisticated, we began to grasp the true immensity of the cosmic population. In the 1990s, the Hubble Space Telescope, our eye in the sky, revolutionized our understanding of the universe. One of its most profound observations came from a seemingly empty patch of sky in the constellation Ursa Major. This region, seemingly devoid of stars and galaxies, would become a window into the universe's hidden depths. In 1995, the Hubble Space Telescope was pointed at this seemingly unremarkable patch of sky for 10 consecutive days, capturing light from the faintest and most distant objects ever observed. The resulting image, known as the Hubble Deep Field, was breathtaking. Instead of an empty void, it revealed a tapestry of thousands of galaxies, each a swirling island of stars, gas, and dust. This single image, captured from a tiny portion of the sky, revolutionized our understanding of the universe's scale. It demonstrated that galaxies are not scattered sparsely throughout the cosmos, but rather clustered together in vast cosmic structures, separated by immense voids. The Hubble Deep Field was just the beginning. Subsequent observations with Hubble and other powerful telescopes, such as the Chandra X-ray Observatory and the Spitzer Space Telescope, have peered even deeper into the universe, revealing even fainter and more distant galaxies. The Hubble Deep Field and subsequent deep field observations provided a crucial piece of the puzzle, a representative sample of the universe. By counting the number of galaxies in this small patch of sky and extrapolating outward, astronomers could estimate the total number of galaxies in the observable universe. Imagine you're holding a grain of sand at arm's length. That tiny grain covers a minuscule fraction of your entire field of view. However, by knowing the size of the grain and the area it covers, you could, in principle, estimate the number of grains on an entire beach. Astronomers use a similar principle to estimate the number of galaxies. By analyzing the distribution of galaxies in deep field images, they can extrapolate these observations to the entire sky, accounting for the fact that the universe is thought to be relatively uniform on the largest scales. Based on these observations and calculations, astronomers now estimate that there are trillions of galaxies in the observable universe. To put that number into perspective, if you were to count one galaxy per second, it would take you over 30 billion years to count them all, longer than the age of the universe itself. This mind-boggling number highlights the vastness of the cosmos and our relatively insignificant place within it. Our own galaxy, the Milky Way, is just one among trillions, each with its own unique history, structure, and population of stars. The sheer abundance of galaxies has profound implications for our understanding of the universe and the potential for life beyond Earth. With trillions of galaxies, each containing billions of stars, the number of planets in the observable universe is truly astronomical. Our journey to count galaxies begins with telescopes. From backyard telescopes to the Hubble, they capture faint light from distant objects. Telescopes collect and focus light, much like our eyes. Larger mirrors or lenses gather more light, revealing distant objects. Spectrographs split light into colors, like a prism creating a rainbow. Analyzing spectra reveals a galaxy's composition, distance, and motion. Determining the distance to faraway galaxies is crucial for estimating their number. One of the key tools astronomers use is the concept of redshift. As the universe expands, galaxies are carried away from each other, and the light they emit gets stretched, shifting towards longer, redder wavelengths. Imagine the sound of a siren as an ambulance races past. As the ambulance moves away, the sound waves stretch out, causing the pitch to drop. Similarly, light waves from distant galaxies stretch as they travel through the expanding universe, causing their light to redden. The farther away a galaxy, the greater its redshift. By measuring the redshift of a galaxy's light, astronomers can calculate its recession velocity, how fast it's moving away from us, and, using Hubble's law, estimate its distance. Hubble's law, a cornerstone of modern cosmology, states that a galaxy's recession velocity is directly proportional to its distance. Armed with powerful telescopes, astronomers embark on deep field surveys to capture the faintest and most distant galaxies. These surveys involve pointing a telescope at a seemingly empty region of space and collecting light for hours. The Hubble Ultra Deep Field is an iconic survey, revealing an estimated 10,000 galaxies. Deep field surveys offer a glimpse into the universe's history, showing the cosmos as it was billions of years ago. In addition to telescopes and deep field surveys, astronomers have another trick up their sleeves: gravitational lensing. This phenomenon, predicted by Einstein's theory of general relativity, occurs when the gravity of a massive object, such as a galaxy cluster, bends and magnifies the light from more distant objects behind it. Imagine, if you will, a magnifying glass held in front of a candle. The lens bends the light rays, creating a larger, brighter image of the flame. Similarly, massive galaxy clusters can act as cosmic lenses, distorting and amplifying the light from galaxies located far behind them. Gravitational lensing not only reveals incredibly faint and distant galaxies that would otherwise be invisible, but also provides valuable information about the distribution of dark matter, the invisible substance that makes up the majority of the universe's mass. By studying how light bends around galaxy clusters, astronomers can map the distribution of dark matter and gain insights into its elusive nature. Astronomical observations are like time machines, letting us witness the universe as it was billions of years ago. By studying distant galaxies, astronomers piece together the history of galaxy formation and evolution. Early galaxies were smaller and less structured than modern ones. Over billions of years, protogalaxies collided and merged, forming new stars and shaping today's galaxies. These observations reveal how galaxies have grown, changed, and interacted over cosmic time. Galaxies are not static islands in space, but rather dynamic entities locked in a constant dance of gravity. As galaxies move through the cosmos, their gravitational pull can draw them together, resulting in spectacular collisions and mergers that reshape their structures and destinies. These galactic encounters are not head-on crashes, but rather drawn-out affairs, lasting hundreds of millions of years. As galaxies approach each other, their gravitational forces distort their shapes, pulling out long streams of stars and gas, creating tidal tails that stretch across vast distances. As the galaxies merge, their gas clouds collide, triggering intense bursts of star formation. These starburst galaxies shine brightly, illuminating the surrounding cosmos with the light of millions of newborn stars. Over time, the merging galaxies settle into a new equilibrium, their individual identities subsumed into a single, larger galaxy. At the heart of most, if not all, massive galaxies lies a sleeping giant, a supermassive black hole, millions or even billions of times more massive than our Sun. These gravitational behemoths, once thought to be cosmic oddities, are now recognized as fundamental components of galaxy formation and evolution. Supermassive black holes grow by accreting surrounding gas and dust, forming a swirling disk of material that heats up and emits intense radiation, creating what astronomers call active galactic nuclei, or AGN. These AGN can outshine their host galaxies, making them visible across vast cosmic distances. While supermassive black holes are invisible to telescopes that detect light, their presence can be inferred from their gravitational influence on surrounding stars and gas. By studying the motions of stars orbiting close to the galactic center, astronomers can calculate the mass of the hidden black hole. Galaxies are not scattered randomly throughout the universe, but rather reside in a vast cosmic web, a network of filaments and voids that stretches across billions of light years. This web-like structure, formed by the gravitational pull of dark matter, provides a scaffolding for galaxy formation and evolution. Imagine a spider web glistening with dew in the morning light. The strands of silk represent the filaments of dark matter, while the dewdrops clinging to the web symbolize galaxies. Just as the dewdrops collect along the web's strands, galaxies tend to cluster along the filaments of the cosmic web. The cosmic web is not static, but rather constantly evolving as gravity draws matter together. Galaxies flow along the filaments, drawn towards massive clusters where hundreds or even thousands of galaxies congregate. These clusters, the largest gravitationally bound structures in the universe, represent the densest nodes in the cosmic web. Within the vast, swirling galaxies scattered across the cosmos, a celestial ballet unfolds. Stars, the building blocks of galaxies, and the celestial furnaces that forge the elements essential for life, are born within immense clouds of gas and dust known as nebula. These stellar nurseries, often spanning hundreds of light years, are the cosmic wombs where gravity draws together interstellar gas and dust, slowly collapsing these clouds over eons. As the material collapses, it heats up, creating dense cores where temperatures and pressures soar to unimaginable levels. When the core reaches a critical temperature of about 10 million degrees Celsius, nuclear fusion ignites, fusing hydrogen atoms into helium and releasing a tremendous amount of energy. This burst of energy halts the collapse, creating a stable star that will shine for millions, billions, or even trillions of years, depending on its mass. Just as galaxies come in a variety of shapes and sizes, so too do their stellar populations. Spiral galaxies, with their graceful arms and central bulges, harbor a mix of young and old stars. The spiral arms, rich in gas and dust, are sites of active star formation, while the central bulges contain older, redder stars. Elliptical galaxies, on the other hand, are generally older and more massive than spiral galaxies. They lack the gas and dust needed for widespread star formation and are populated primarily by old red stars, giving them a reddish hue. Irregular galaxies, as their name suggests, lack a defined shape and often result from galactic collisions or interactions. These galactic mergers can trigger intense bursts of star formation, creating a diverse population of stars of different ages and masses. Estimating the number of stars in a galaxy might seem like an impossible task, like counting grains of sand on a beach. However, astronomers have developed clever techniques to estimate these astronomical numbers, relying on observations of a galaxy's brightness, mass, and the types of stars it contains. One method involves measuring a galaxy's total luminosity, the amount of energy it emits as light. By comparing this luminosity to the known brightness of different types of stars, astronomers can estimate the number of stars of each type that would be needed to produce the observed light. Another method involves studying a galaxy's rotation curve, the way in which the orbital speeds of stars vary with their distance from the galactic center. By analyzing these rotation curves, astronomers can infer the distribution of mass within a galaxy, including the mass of its stars. Our Milky Way galaxy contains hundreds of billions of stars, perhaps as many as 400 billion. And remember, the Milky Way is just one among trillions of galaxies in the observable universe. A conservative estimate for the total number of stars in the observable universe is 10 to the power of 24 stars. The sheer abundance of stars has profound implications for our understanding of our place in the cosmos. As we contemplate the staggering number of galaxies and stars that populate the universe, a sense of awe and humility washes over us. Our home planet, Earth, a pale blue dot orbiting an average star, shrinks to an almost unimaginable insignificance amidst this cosmic ocean of celestial wonders. The sheer scale of the universe, with its trillions of galaxies, each harboring billions upon billions of stars, challenges our very notion of perspective. It underscores the fact that we are but a small part of something much grander, a cosmic tapestry woven together by gravity, time, and the fundamental laws of physics. Yet, within this vastness, we find ourselves endowed with the remarkable capacity to question, to explore, and to seek understanding. We have, through the ingenuity of science and the power of human curiosity, begun to unravel the mysteries of the cosmos, piecing together the story of the universe from its fiery birth to the present day. The cosmic perspective, born from this understanding of our place in the universe, instills in us a sense of humility, awe, and inspiration. Humility, because it reminds us that we are not the center of creation, but rather inhabitants of a tiny planet orbiting an average star in a galaxy teeming with billions of other stars. Awe, because it fills us with a sense of wonder and amazement at the sheer scale, beauty, and complexity of the universe. From the swirling arms of spiral galaxies to the fiery births and deaths of stars, the cosmos is a never-ending source of wonder and fascination. And inspiration, because it challenges us to push the boundaries of human knowledge and understanding. Knowing that there is so much more to explore, so many unanswered questions, ignites a spark of curiosity within us, driving us to seek answers and explore the universe around us. The quest to understand the universe is a journey without end, driven by our innate curiosity and thirst for knowledge. With each discovery, we reveal more wonders and mysteries to ponder. The future holds the promise of even greater discoveries as we develop new telescopes. We stand on the threshold of a new era of cosmic exploration. Are we